Alright guys, welcome back to Underground Science, and in this video we're going to do another hydrohalogenation example, but this time it's going to involve another carbocation rearrangement that we should always look out for. So let's dive into an example right away. So now that we're familiar, right, with what the nucleophile, electrophile is and how to draw the mechanism, this can hopefully go a little bit quicker, right, because now we're more familiar with it. So if we drew the reactants and the reagent, hydroiodic acid, it's a strong acid, but it would actually help us if we actually drew the bonds out, right? So nucleophile attacks the hydrogen, this bond breaks, goes on the iodine, making the iodide anion, and then that would look something like this next. So we have two methyl bonds here, going down here, and then this would be the new bond, okay? This would be the new bond right there, and then you would have the iodide anion. And then because this carbon over here lost an electron, right, because this is an electron for this carbon and it lost that while making the bond to this hydrogen, we're going to have a positive charge on this carbon then. And then now, right, so remember this is basically an empty p orbital. So it's like it needs an electron, or it needs a bond, I should say, right? Let's draw a better p orbital. Because it's an empty p orbital, iodide, again, as we know, can attack either from the bottom or the top, but we won't focus on that right now. We'll just focus on the fact that iodide, this is a good environment, an electron poor area, in which iodide can attack and make a bond. So the next step will look something like this, in which we will make a bond. So this will be the bond to hydrogen, and then we'll make a bond. Okay, let's pay attention, draw the methyls here. And then we made a bond to this carbon, right? So that's the iodine bound to that carbon. So we would think this is the product, right? Based on if we weren't focusing on any carbocation rearrangements. Because this is what we would think happens. But now let's go into reality, right? And what actually happens is this. So this double bond will attack this hydrogen. This bond will break, leading to the next intermediate, which is going to be like that, with a iodide anion. Now, remember, this carbon, this carbocation specifically, is a secondary carbocation. However, what if I moved this methyl next door, right, over here? Then I would have this. Right? Now, the cation would be on this carbon. Now, in particularly, this carbon specifically, I should say, is going to be a tertiary carbon now. So what we have to decide now is who's better, a tertiary carbocation or a secondary carbocation. And of course, the answer is a tertiary carbocation, right? That's more stable. And so we have to choose this intermediate, not the one, not right here. This won't be the right product because we never chose the more stable carbocation. This was a secondary carbocation, but we had the option of making this a tertiary carbocation over here if we just moved the methyl. Okay, so because we moved the methyl like right next door, this is called a 1,2 methyl shift. Okay, 1,2 methyl shift. Okay, so now that we have this right here, right, this right here, let's continue from here and talk about what happens next. So what happens next is, now that we have a carbocation here, this is an electron poor area, so this is going to act like the electrophile. In the nucleophile, an electron-rich molecule, or an atom in this case, is going to attack the electrophile and make a bond. So next what's going to happen is we're going to have this molecule right here. Let's draw out the atoms. And then this iodide, again, we said was going to attack here, which would make the bond become right there on that carbon. And this would be our product. Now let's compare this to the product we had right here when we did not consider a carbocation rearrangement, right? So the difference is that in this product, we made the iodide attack this carbocation right here, make a bond to this carbon, but we did not consider the methyl shift, making this the better and more stable carbocation. Alright, so that's it for this video. In the next video, we're going to start talking about anti-Markovnikov addition, however, still relating to hydrohalogenation. Alright, so I hope to see you guys there.